Today we will discuss the theory of bipolar transistor. Simple diodes are made up from two pieces of semiconductor material to form a simple p-n junction. If we now join together two individual signal diodes back to back, this will give us two p-n junctions connected together in series that share a common p or n terminal. The fusion of these two diodes produces a three-layer, two-junction, three-terminal device forming the basis of a bipolar junction transistor, or BJT for short. Transistors are three-terminal active devices made from different semiconductor materials that can act as either an insulator or a conductor by the application of a small signal voltage. The transistor's ability to change between these two states enables it to have two basic functions: switching, digital electronics, or amplification, analog electronics. Then bipolar transistors have the ability to operate within three different regions. Active region: the transistor operates as an amplifier. Saturation: the transistor is fully on, operating as a switch. Cutoff: the transistor is fully off, operating as a switch. The word transistor is a combination of the two words transistor, which describes their mode of operation way back in their early days of electronics development. Bipolar transistors are current-regulating devices that control the amount of current flowing through them in proportion to the amount of biasing voltage applied to their base terminal, acting like a current-controlled switch. The principle of operation of the two transistor types PNP and NPN is exactly the same, the only difference being in their biasing and the polarity of the power supply for each type. The direction of the arrow always points from the positive p-type region to the negative n-type region for both transistor types, exactly the same as for the standard diode symbol. As the bipolar transistor is a three-terminal device, there are basically three possible ways to connect it within an electronic circuit, with one terminal being common to both the input and output. Common base configuration has voltage gain but no current gain. Common emitter configuration has both current and voltage gain. Common collector configuration has current gain but no voltage gain. The common base configuration. As its name suggests, in the common base or grounded base configuration, the base connection is common to both the input signal and the output signal. The input signal is applied between the transistor's base and the emitter terminals, while the corresponding output signal is taken from between the base and the collector terminals as shown. The base terminal is grounded or can be connected to some fixed reference voltage point. The input current flowing into the emitter is quite large, as it's the sum of both the base current and collector current respectively. Therefore, the collector current output is less than the emitter current input, resulting in a current gain for this type of circuit of unity or less. In other words, the common base configuration attenuates the input signal. This type of amplifier configuration is a non-inverting voltage amplifier circuit. This type of transistor arrangement is not very common due to its unusually high voltage gain characteristics. Its input characteristics represent that of a forward-biased diode, while the output characteristics represent that of an illuminated photodiode. Also, this type of bipolar transistor configuration has a high ratio of output to input resistance, or more importantly load resistance to input resistance, giving it a value of resistance gain. Then the voltage gain for a common base configuration is therefore given as, where IC over IE is the current gain, alpha and RL over Rn is the resistance gain. The common base circuit is generally only used in single-stage amplifier circuits such as microphone preamplifier or radio frequency RF amplifiers due to its very good high-frequency response. The common emitter configuration. In the common emitter or grounded emitter configuration, the input signal is applied between the base and the emitter, while the output is taken from between the collector and the emitter as shown. This type of configuration is the most commonly used circuit for transistor-based amplifiers and which represents the normal method of bipolar transistor connection. The common emitter amplifier configuration produces the highest current and power gain of all the three bipolar transistor configurations. This is mainly because the input impedance is low, as it is connected to a forward-biased p-n junction, while the output impedance is high as it is taken from a reverse-biased p-n junction. As the load resistance is connected in series with the collector, the current gain of the common emitter transistor configuration is quite large, as it is the ratio of IC over IB. A transistor's current gain is given the Greek symbol of beta. As the emitter current for a common emitter configuration is defined as IE equals IC plus IB, the ratio of IC over IE is called alpha, given the Greek symbol of alpha. Note that the value of alpha will always be less than unity. Since the electrical relationship between these three currents, IB, IC and IE, is determined by the physical construction of the transistor itself, any small change in the base current will result in a much larger change in the collector current. Then, small changes in current flowing in the base will thus control the current in the emitter-collector circuit. Typically, beta has a value between 20 and 200 for most general-purpose transistors. So if a transistor has a beta value of say 100, then 1 electron will flow from the base terminal for every 100 electrons flowing between the emitter-collector terminal. By combining the expressions for both alpha and beta, the mathematical relationship between these parameters and therefore the current gain of the transistor can be given as. This type of bipolar transistor configuration has a greater input impedance, current and power gain than that of the common base configuration, but its voltage gain is much lower. The common emitter configuration is an inverting amplifier circuit. This means that the resulting output signal is 180° out of phase with the input voltage signal. In the common collector or grounded collector configuration, the collector is now common through the supply. The input signal is connected directly to the base, while the output is taken from the emitter load as shown. This type of configuration is commonly known as a voltage follower or emitter follower circuit. The common collector or emitter follower configuration is very useful for impedance matching applications because of the very high input impedance, in the region of hundreds of thousands of ohms, while having a relatively low output impedance. The common emitter configuration has a current gain approximately equal to the beta value of the transistor itself. In the common collector configuration, the load resistance is situated in series with the emitter, so its current is equal to that of the emitter current. As the emitter current is the combination of the collector and the base current combined, the load resistance in this type of transistor configuration also has both the collector current and the input current of the base flowing through it. Then the current gain of the circuit is given as. The common collector current gain is. This type of bipolar transistor configuration is a non-inverting circuit in that the signal voltages of V in and V out are in phase. It has a voltage gain that is always less than unity. The load resistance of the common collector transistor receives both the base and collector currents, giving a large current gain, as with the common emitter configuration, therefore, providing good current amplification with very little voltage gain. We can now summarize the various relationships between the transistor's individual DC currents flowing through each leg and its DC current gains given above in the following table. With the generalized characteristics of the different transistor configurations given in the following table. Hope you understood the theory of bipolar transistor easily. Goodbye from us.